today's agenda, this presentation course. And then next up is Michaela Guiney. Michaela is a co-architect of our change team and runs the OA team at Cadence. So she's about the most knowledgeable person about 2260. And here's Michaela.
Great, thank you. I'm going to do a brief introduction of OA. Hopefully everybody already knows what it is, but it never hurts to kind of review what it is. Go through some discussion of its evolution over time, the current challenge, and then how 2260 helps address the challenges of IC design today. So open access is an SI2 standard API that's used to represent IC design, from logical net through tape-out. There is a reference implementation available to SI2 and OAC members, including both documentation and source code. And open access can provide a very good basis for an applications in-memory data model. It provides high performance, minimal memory usage, has an efficient object-oriented API, and has extensions built in so that you can decorate open access objects with information that's important to your application. And probably most importantly is it's been qualified in a number of high-end commercial EDA tools, so it's not a toy piece of code. It's code that has stood the test of time with real users. Now, open access has been out there for longer than I'd like to say because it dates me, but it's been in general use for over 15 years. So the question is, how has it managed to stay relevant and continue to meet people's needs? Well, there were two particular features built in that I think have enabled this. One is API compatibility and feature-based compatibility. So by API compatibility, we mean that within a given stream, like the 2250 stream, OA APIs are always kept drop-in compatible, which means over, say, the 2 or 3 year lifetime of an open access stream like 2250, we never change any of the API signatures unless we're adding on a new parameter, which means your applications will continue to run. If you drop in a new version of the OA shared libraries, your applications will generally continue to run. The other feature is feature-based compatibility, and that means that when we add a new kind of piece of data, and we'll talk about an example later on in the presentation, we tag the databases as having that new feature so that open access itself can provide a clean indication to an application that this piece of data has data in it that you don't understand, so you can't open it. So that's really allowed older applications to continue to function in flows for longer because they can tell what data they are able to use and what data they're not able to use. Those two features, I think, have been critical to allowing OA to evolve over time and the applications based on them, so that the flows used by our customers can remain stable. And as proof of that statement, we have, over the last 14 years, released over 100 releases of open access. We've introduced 5 new data models with various new features in each of them, and introduced new functionality, performance improvements, and bug fixes in those various releases. So here's kind of a quick view over time of the different releases of open access over the years and the new capabilities provided. Way back in 2005, we came up with our first new data model, which allowed us to represent more shapes, more than 4 gigs worth of shapes. We introduced big groups and incremental technology databases and new types of constraints in 2006. In 2007, we provided a PCL plugin and enhancements to constraints. In 2008, we provided a way to very quickly switch out from one version of a master to another. In 2009, we expanded undo to the technology database. We implemented Uniquify, which is harder than it sounds, change management, and a plugin for the libdef file. In 2010, we provided new initial models for multi-threading and more constraint capabilities. In 2011, we created a new database format, which on disk, which reduces the size of your data files substantially, and for people with slower networks can really improve your read time, more constraints. 2012, scratch designs and designs you don't have to commit to disk, and app defs that aren't undoable, which can make them much faster. In 14, we came up with DM5, which allowed us to create larger string and name tables, which meant that very large Verilog files could be imported into OA. In 2015, we enabled wrong-way routing in DEF, which is, again, a little more complicated than it sounds. And we also came up with a way to let applications know that they're doing inappropriate things in observers, which can cause a lot of crashes. And in 2016, some conflict observers for app defs and trim metal support, which is also harder than it sounds. But it was very important for SADP type process technologies. So what was our next step? Well, there is, I think it's a rule, there's really no EDA presentation that can't include in the words, chip data is getting bigger, and this one's no exception. We've been fighting this battle since the dawn of EDA. So what are we going to do about it this time? Well, one new tool that we have at our disposal is the cloud. And within the cloud, we have great availability of big multiprocessor machines available to the average designer when they need it. So we thought, why don't we try to enhance OA to provide finer granularity access for the parallel processing that's a lot easier for designers to get to these days. So we decided to build on an existing capability in OA. Since very early on in OA's history, we've had the ability to partially read an open access database. Specifically, if all your application cares about are nets, when you read a net, you read in all the nets, but you don't read in all the shapes or all the vias. And if you're only interested in shapes and vias, then you don't read in nets. And that's built into the Open Access API. If you never traverse the collection of nets off of a OA block, you just don't read them in if the data is big enough. The problem is, though, is that if you want one net or one shape or one via, you end up reading them all. So what we decided to create was the ability for applications to organize their data in the way that they need in order to achieve the capacity and performance improvements that they're looking for. And then you'd be able to, for example, access just the data you need from one of several processes running in parallel. So the way that we're enabling that is a new class in Open Access called OA Partitions. And they provide an infrastructure that allows applications to determine or to specify how they want data to be loaded from disk. So the application itself can take objects of a given type and divide them up into different OA partitions, and then later load those individual partitions one by one to improve their performance and capacity. Now, because OA partitions are a new class, they're a new database type of database object, and that triggers a new data model, which we are calling DM6. Now, for those of you who are nervous about having to deal with a new data object or having your data automatically upgraded to 2260, don't worry about it. You have to run an application that explicitly creates them. So if you just read in a DM5 design with OA 2260 and save it, it's not going to get upgraded to DM6. Your application has to explicitly create these partitions. So that said, let's look at an example for how one might use OA partitions. Say that you wanted to partition all of your shapes into tiles for some sort of distributed processing analysis. So in a very simple example, you would take a given design. You had 16 processors available to you, and you wanted to be able to split the data up into and assign one processor to a subset of the data. So you want each process to access just the shapes in one of these tiles. So your application would have to create a partitioning strategy and implement it. So one very simple-minded algorithm is just determine the bounding box of the design, divide the shapes in the design into 16 different partitions based on the shape's low or left point. You'd probably have to come up with a strategy for the shapes to span tiles, but this is a simple-minded strategy. So then after you'd partitioned the data and you wanted to analyze the design, you would start a master process, which would launch 16 separate parallel processes running in memory on different processors, and then for each process I, you'd load the shapes from partition I and analyze those shapes. So if you as an application are explicitly taking advantage of partitioning, you should see some substantially improved performance when reading DM6 data. So for example, you could be like potentially 10 times faster if you're distributing your work over 16 processors. However, on 2260, if you're reading, writing, and accessing DM5 data, you're not going to see any change in performance or capacity. Something that should be noted is the first time that you save a partitioned DM6 database, it is going to be slower than the DM5 save, because this is the point of save where we take all the data that's in partitions and save them out into separate parts of the data file. So that does take longer. But when you save thereafter, it should be comparable to an existing DM5 save, unless you've completely reworked all of your data and it's essentially having to recreate all these partitions. Also note that, of course, because we have to store partition information, the size of data on disk will increase somewhat. So in summary, OA partitions have been built in order to allow applications to partition their data, to control how much data a given process has to load, and it provides opportunities, therefore, for these applications to use less memory and to run faster. Now, while we were at it, we had some customer bug reports and SI2 bug reports where applications were running out of room for two different types of data. We had some reports of people who were trying to create, I think they were trying to import through Stream data that had OPC data associated with it, so it had tons of polygons, and they were running into the 4 gig limit on point data. I think there was also an application that, and I don't think that they meant to do this, but they were creating a lot of OA app props, and they had hit the 4 gig limit. So we've eliminated that limit on both of these data types, and they now can access tables that instead of a 4 byte wide index, it's an 8 byte. It can be up to an 8 byte wide index. There are no application level changes to enable this. This is all internal to open access. Again, reading in a DM5 database and saving it out isn't going to cause these tables to be increased in size. It'll only, so that if you save a database, it'll still be DM5. The only time you'll be marked as DM6 because of these changes if you actually have data with more than 4 gig worth of point or app prop data. So I wanted to say a little something about which platforms are supported in 2260. We've moved to Visual Studio 2015 on Windows, although I think our install notes for 2260.005 were incorrect about this. That's being fixed in our next release. And also we're moving to GCC 6.3 on Red Hat 6.0. So if you are providing a plugin or using a plugin, you need to recompile that plugin on the new compiler in order to be able to run with the new OA 2260 shared libraries, and in particular the new GCC runtime library. So if you want to continue to run with 2250, you're fine, but if you want to run with 2260, you got to recompile, and you got to recompile your plugin. We're also pairing 2260 with the a new version of LeftF parser, which has also been provided to SI2. That's version v5.8 underbar 60 T001. We've also moved on to TICL 8.6. And the OA installation guide has more information on the other dependencies like Bison and Flex. And again, if you want to start working with OA 2260, if you want to use partitions, you need to create partitions and add objects to them. And then during editing, you'll need to register observers to move objects to the right partition, say if they are modified in a way that might mean that they belong to a different partition. They'll be automatically, if you delete objects, they'll be automatically removed from partitions. But if you create them or modify them, you need to make sure as an application that they go into the right partition for you. Now, if you don't want to explicitly use our OA partitions, all you need to do is recompile. There's no application level changes if you're not using OA partitions. There's no application level changes for the increased point or outprop data capacity changes. Okay, just to wrap it up, Cadence has contributed 2260 to SI2, and it's available to the SI2 OA Coalition members. And we think it continues the tradition of providing a stable platform for IC design applications while still evolving to meet the new challenges that the chip design folks keep sending our way. Any questions?
If I have a DM6 partitions design and I rerun my legacy code on it that was written for DM5, is there any inherent improvement that you would pick up just from the tables being more readily available?
Well, if you haven't recompiled your legacy application with 2260 headers, then when you attempt to read it, you're going to be told it as a feature that you don't understand. However, if you have recompiled, but you don't explicitly understand the partitions, you may benefit because there's just like in partial load today, if you traverse just the shape list, that's all you get. There's also an implicit loading of partitions. So say that as you walk through the shapes in the design's list of shapes, you walk through a subset of them, and it turns out that's all the information you need, and you end up only loading a subset of the shape data. Like a good example might be you're interested only in the shapes associated with pins, and it's a massive design, but you only care about the shapes associated with pins. Well, if somebody's partitioned the data, the shape data, odds are you're only going to load a subset of the partition, and that will improve your capacity and it will improve your performance. So you can benefit without actually having to do any of the work if somebody else has partitioned it.
All right.
One more question.
Mm-hmm.
Do you see this possible? I see this as very powerful, but let's assume I give someone an IP block as an OASIS file. All the partitioning, all the effort I spent in partitioning this is gone, right? One way of keeping the partition information persistent would be, for instance, adding properties to an OASIS file or some other way so that someone else with the same data model could read in the original partition.
Sure.
Do you see this as being possible? Because, I spend all the effort of partitioning my designs, and the moment I give it out to someone else, it's gone, right?
Yeah, you could do that. You could build the smarts of partitioning into your OASIS translator.
Yeah. Because this would be really cool if this would be persistent across, I mean, even if I give someone an OASIS file.
Yeah.
So a follow-up question to that, Michaela. It's Fred from Sabaco.
Okay.
Does this kind of break interoperability, since the control of the shapes in the partitions is application specific? If another application goes and modifies shapes, then would we potentially be impacting another tool's ability to read the data correctly because we violated their partitioning structure?
I would say that two things. First of all, you're always going to be able to read all the data. You may not be able to trust your partitions are working the way you expected them to, but you can always trust that the data there's no problem with the data itself. It's just really an organizational structure on top of the data. But if I were an application writing partitions, I would probably do things like save the last modified timestamp of the data that I used to, the last modification timestamp before I completed the save with partitions. And when I read that design back in and I realized somebody's done an out of context modification, then I would know to proceed with caution.
Okay, so it's advised that all editing applications that utilize partitions check some form of timestamp like that and potentially rebuild their partitions.
Right. Now,
Okay.
and new data that's created without knowledge of partitions, I think gets shoved into another partition that you can. I think you can get to that data explicitly, but a piece of data that's been modified that in a way that means that it doesn't really belong to that partition anymore, we don't have a good way of flagging those particular set of objects to you. So that's where you'd have to proceed with caution or rebuild.
Mm-hmm. Thank you.
Sure.
Hi, I also have a question. My name is Patrick Leck, and I'm calling from Mentor Graphics. I would like to understand a little bit better what the relationship is between the partitions and the block. So is a block divided into a number of partitions, or does each of the partition have a block? So basically, if you iterate through shapes in a block, are you going to span multiple partitions, or is it the other way around?
So a block will have a list of partitions. Actually, I think the design has a list of partitions. You can't have a partition with shapes in it, for example, in more than one design. So all the partitions belonging to a design have to contain objects that also belong to the design. Does that answer your question?
Yes, I understand. Okay. So basically the block can be divided into individual partitions, and then, and
Correct.
then you can analyze the shapes in each of the partitions individually. Mm-hmm.
Right. But you still have the ability to iterate directly from a OA block to all the shapes in the OA block without going through the partition.
Got it. Mm-hmm. And OA will automatically fetch data from the database as needed.
Right. That's the implicit load that people can potentially benefit from without having explicitly created partitions or come to understand them at all.
Got it. Yes, that makes perfect sense. One more question. So in the example of partitioning a design, you've shown a large design that was partitioned into these 16 individual partitions. Do you envision partitions potentially overlapping each other? Say customers putting, a subset of layers into one partition and another subset of layers in another, and those two partitions overlapping, or do you envision them being? Yeah. Okay.
I mean, you can kind of do whatever you want, as long as the thing to bear in mind is that in a given OA partition, there can only be objects of a single type. It's not like you can throw all the nets or all the shapes and all the vias into the same partition. You're going to have your shape partitions. You're going to have your separate via partitions. But,
okay.
You can manage them so that you can think of them as like a stack if you're going to be organizing them geometrically.
Got it. Mm-hmm. Thank you.
Sure.
Hi, it's Christian from Synopsys. One quick question. Can there be multiple partition schemes for one design, or does it only have one partition scheme?
A given object can belong to one partition only. So you can have one scheme dealing with geometric data and a different scheme dealing with nets, but a given shape has to belong to one partition. So I don't know that you could have like multiple schemes for shapes at the same time.
And how is that enforced? Is it through exceptions or some kind of error system?
I think it would be an exception if you tried to add an object to a partition that was already in a partition. Yeah. I just double checked. If you try to add an object to a partition and it's already in a partition, you're going to get an error back, an exception.
Thank you.
And then one more follow-up question to that. So did you say that there may be partitions which will contain net information?
Yeah, you could have, I was just saying you could have a bunch of partitions that organize your nets, and you could have another set of partitions that organize your shapes, and you could have another set of partitions that organize your vias.
Right, okay. And then when you browse the partition that contains the net information, you can still retrieve shape, references to shape which make up a given net, which would which would live in a different partition.
Correct. And you can use your normal OA APIs to do that. And if you're accessing a shape that's in a partition that hasn't yet been loaded, OA will automatically do that.
Great. Thank you. Thanks for clarifying.
Now, bear in mind, not every single object has been enabled for partitions. Shapes have been, vias have been. I think we did nets. I'll have to double check on that.
Okay. Thank you.
Thank you, Michaela. It's a great presentation.